welcome back to the second session on neural networks. In the first part of neural networks, we had an introductory discussion about biological neuron and artificial neuron. We have introduced a very basic neural unit known as Macular-Pitts neuron or MP neuron. Today, let us have a recap of our earlier discussion and then we'll proceed with perceptron. In the previous session, we had a discussion about the biological neuron and the very basic neural unit known as Macular-Pitts neuron or MP neuron. So let us list out how the biological neuron is analogous to artificial neuron. So let us see on this slide a picture of a biological neuron wherein we are having the important components or parts of biological neuron such as cell body, dendrites, axons, axon terminals and so on. On the right hand side of the slide, let us have a look towards the MP neuron. So here we have a node, the inputs, the interconnections and the output. So let us look at the terminologies. Those are analogous in biological neuron and artificial neuron. In biological neuron, we have cell body with nucleus or also called as soma, whereas in artificial neuron we have a node. In biological neuron we have dendrites. Those actually receive the input signals. So here in MP neuron we are having the inputs denoted here as x1, x2 up to xn, and we said that these inputs are binary inputs. In biological neurons we have synapse or axon terminals. Those are actually the points of connection to other neurons. Equivalently, in artificial neurons we have weights or interconnections. In case of MP neuron, we are having similar importance for all the inputs. So weights are associated with value 1 and hence those are not been depicted in this figure. In biological neurons we are having the axons. These are actually transmitting the outputs, whereas in artificial neurons we are having the output denoted here as Y. In the previous session, at the end, we listed 4 limitations of MP neuron, and we mentioned to overcome these limitations we are having a new kind of neural unit, and that is known as perceptron. So prior to actually dealing with perceptron, let us once again go through these limitations and understand the problems. So the first limitation of MP neuron is the type of input that is handled by MP neuron. MP neuron handles only Boolean kind of data. Please remember, MP neuron handles only Boolean kind of data. So how to deal with non-Boolean, say for example real inputs, and that is the question number 1 or limitation number 1 of MP neuron. In MP neuron, if you remember, we dealt with one problem or one example rather that deals with decision whether to go for watching a movie or not, and we had the binary inputs. Say for example, we had the input whether the movie is thriller having only 2 values, yes or no, 1 or 0, or whether director is X, actor is Y, and so on. So all those inputs were Boolean, having the values 1 and 0. But now let us consider another example in medical diagnosis. We have discussed a similar problem earlier. Let us assume that we have been provided with the data, and every instance in the data set describes the properties of the tumor, such as tumor size, perimeter, color, some textural properties, and so on. So here many of the features are non-Boolean. Tumor size is a real number. Textural properties are also real. Perimeter is also real. Color may have some discrete values. So now, based on these features, we are supposed to classify the tumor whether it is malignant or non-malignant, or whether it is malignant or benign. Malignant means cancerous, benign means non-cancerous. So we are having the binary classification based on these features, which are non-Boolean. Obviously, MP neuron may not help us to solve this problem, and that is why we need to look for some alternative. The second limitation is that do we always need to hand code the threshold? In the last class, whenever we dealt with some Boolean functions like and, or, what we did? We used the hand coded thresholds based on the inputs and the function that we are implementing. If the problem is simple, then it is possible, but it is not really good for the complex problems with high dimensional data sets. So we need a mechanism to learn this threshold instead of hand coding it manually. Now let us go to the third problem. Whether all inputs are having equal importance. What if we want to assign more importance to some inputs? In MP neuron, all the inputs are weighted equally, but sometimes what happens is some features or attributes are more important than other attributes. For example, returning back to our movie example, if the feature, say, is director X, only matters to decide whether to watch the movie or not, it should be given high weightage or importance. So once again, to handle this issue, we need to look for some better mechanism. The fourth question that we posed was, what about functions which are not linearly separable? Say for example, the Boolean function exclusive OR. To address these questions or to overcome these limitations of the MP neuron, Frank Rosenblatt, an American psychologist, proposed the classic Perceptron model, the mighty artificial neuron, and this was proposed in 1958. It is more generalized computational model than the McCulloch-Pitts neuron, where weights and thresholds can be learned over time. So now let us focus upon our new interest, and that is perceptron. As I mentioned, it was proposed in 1958 by Frank Rosenblatt, and further it is refined and carefully analyzed by Minsky and Peppert in 1969. So, let us see the main differences in MP neuron and perceptron. MP neuron can handle only Boolean inputs, whereas perceptron supports real inputs as well, which makes perceptron more useful and generalized. The next difference, as you can see in this figure, in MP neuron, weights are not available to decide the importance of the respective input, but here in perceptron, introduction of numerical weights is the key difference, with a mechanism to learn these weights. The perceptron has the learning algorithm to learn the parameters like threshold theta and the weights. So these are the main differences between MP neuron and perceptron. Now let us see here how we can formulate the output y. So please see here, we are having the inputs x1, x2 up to xn. Every input is associated with the weight w1, w2 up to wn, that is being fed to the node or neuron. Now here, what neuron is doing? Neuron is having the weighted sum of input. Please recall, in MP neuron we had summation of xi, so we were summing the Boolean inputs, but here in perceptron we are having the weighted sum, summation over I equal to 1 to n wi xi. And now see here in this expression, we are comparing this weighted sum with the threshold theta, and if the sum is more than arbitrary threshold theta, then output y is equal to 1, otherwise it is 0. Let us rewrite these expressions such that now we can compare the expression with 0 instead of theta. So how we are rewriting? Y equal to 1 if summation over I equal to 1 to n wi xi minus theta is greater than or equal to 0, and y equal to 0 if summation over I equal to 1 to n yi xi minus theta is less than 0. I hope you must be agree with this new form of expression. But now what we would like to do is, we would like to further refine this expression such that we are not going to treat this theta separately, but instead, is it possible to add this theta as one of the inputs to the neuron and make a more convenient way of representation, like y equal to 1 if summation I equal to 0 to n wi xi is greater than or equal to 0, and y equal to 0 if summation over I equal to 0 to n wi xi is less than 0. Please note, in this new convention our I varies from 0 to n. So we would like to add this theta as one of the inputs to the neuron, and hence we can add one more input x0, which is always equal to 1, with the associated weight w0 is equal to minus theta. So what we are doing simply is, in this expression minus theta is being replaced with plus w0 x0, and to have the equivalence in between these two terms, we are assigning w0 equal to minus theta and x0 is 1. Makes sense? Thus, this is the most accepted convention of a perceptron. Now let us look at this modified version of our perceptron, where we have added one input x0 which is set to 1, so that means it is always on, and w0 is the associated weight, that is equal to minus theta. So with these settings, now this perceptron is similar to that of MP neuron, but here we are taking now the weighted sum, and that weighted sum is being compared with 0. And one of the inputs, that is x0, is having the associated weight minus theta, which is actually dealing with the threshold. So instead of hand coding the thresholding parameter theta, what we did is we added it as one of the inputs with the weight minus theta as shown here, and this makes this theta learnable. So the limitation that instead of now hand coding the parameter theta, it is possible to learn this theta as well using the perceptron learning algorithm that we are going to discuss later. Here W0 is called as bias. So let us illustrate this model with our movie example. If a person is a movie lover and not very specific about various parameters like who is director, who is actor, etc., then perceptron will have a very low threshold and may watch any movie irrespective of any of the criteria, and hence theta would be equal to 0. On the other hand, a selective viewer may only watch a movie if the specific actor is performing or is directed by a specific director and so on. So the higher value of theta, say for example 2 or more, is suggested. The point is the weights and the bias will depend on the data that is provided as the viewing history of the person in this particular example. Based on the data, if needed, the model may have to give a lot of importance or high weight to the specific input and penalize the weights of other inputs at the same time. And this is what is the procedure of learning the perceptron based on the training data set available. Now let us compare Maculop-Pitts neuron and perceptron. So looking at the diagrammatic representations of both the models, in MP neuron we are having only the Boolean inputs x1, x2 up to xn, whereas perceptron allows non-Boolean inputs as well. In MP neuron, we are not having the weights associated with the inputs, whereas we can weigh the inputs or we can give more importance to few of the inputs than the others in perceptron. So we are having the weights associated with the inputs in perceptron. Similar to that of MP neuron, perceptron can also separate the input space into two halves, positive and negative. All the inputs that produce an output 1 lie on one side, that is positive half space, and all the inputs that produce an output 0 lie on the other side, that is the negative half space. In other words, a single perceptron can only be used to implement linearly separable functions just similar to that of MP neuron. Then you may think, what is the difference and why do we claim that the perceptron is an updated version of MP neuron? The question is really valid. Here in perceptron, we are having the weights associated with the inputs, and the threshold theta is also included as one of the weights, as we can see here in this figure, and also it has been represented using this expression. But please note, here the weights including the threshold can be learned, and the inputs can be the real values also. So I hope you must have understood the difference in MP neuron and perceptron clearly. In the previous session, we have seen how MP neuron can be used to implement Boolean functions. Let us see now how perceptron can also be used to represent Boolean functions. So we are not going for all the Boolean functions, but we'll see the couple of functions as the representatives, and I would suggest that you should try perceptron for implementing other Boolean functions as well. So let us see now the Boolean OR function and how to implement it using perceptron. So let us see this picture showing the perceptron. These are the two inputs, x1, x2 with associated weights w1, w2, and this is the third input is for bias. This perceptron finds the weighted sum, compares it with 0 and produces the output y. Now look at this table that provides the truth table for OR function, and also look at these expressions written in the form of perceptron expressions. For this perceptron to produce the output 0 for inputs 0, 0, it has to satisfy the expression w0 plus summation over I equal to 1 to 2 wi xi less than 0. Similarly, for the inputs 0, 1, 1, 0 and 1, 1, it has to satisfy the expression w0 plus summation over I equal to 1 to 2 wi xi greater than or equal to 0, right? So from this summation we have separated the term w0 x0, and as x0 is always 1, this term becomes w0. I hope you must have understood. Thus, for the expected outputs, these expressions need to be satisfied. In fact, these expressions are depicting the linear inequalities. See here, the first expression becomes w0 plus w1 into 0 plus w2 into 0 less than 0. So this implies the inequality w0 less than 0. So if we provide the inputs, the second expression becomes w0 plus w1 into 0 plus w2 into 1 greater than or equal to 0. So this implies the inequality w2 greater than minus w0. Similarly, look at the third expression written using the third set of inputs. So it becomes w0 plus w1 into 1 plus w2 into 0 greater than or equal to 0, and this implies the inequality w1 greater than minus w0. And now for the last set of inputs 1, 1, the expression becomes w0 plus w1 into 1 plus w2 into 1 greater than or equal to 0. So this implies the inequality w1 plus w2 greater than minus w0. So ultimately we have now the 4 equations or linear inequalities, and it is possible to solve the linear system of inequalities using the algorithms. Those who do not know how to solve the system of inequalities, please refer to the link provided at the bottom of the screen. Now let us see one of the possible solutions after solving this linear system of inequalities. It provides W0 equal to -1, W1 equal to 1.1 and W2 equal to 1.1. Please note, this is only one of the possible solutions. Various other solutions are also possible for this set of inequalities. If we look at the geometrical representation of this OR function in the Boolean space, we have 4 inputs 0, 0, 0, 1, 1, 0 and 1, 1 as shown, and we have the decision boundary represented as W0 x0 plus W1 x1 plus W2 x2 equal to 0. So it is this line -1 plus 1.1 x1 plus 1.1 x2 equal to 0. Thus, it is clear that the solution separates the input space into 2 spaces, negative and positive half spaces, and it differentiates the samples. Once again, I encourage you to try it out for other Boolean functions such as AND, NOT and so on. Now, let us see another Boolean function, that is a function which is non-linear, and this is exclusive OR XOR function. In the similar way that of the OR function, we are having here the truth table for XOR function. So we are having 4 combinations of input x1, x2, and these are 0, 0, 0, 1, 1, 0 and 1, 1. So 0, 0 provides the output 0, 0, 1 provides the output 1, 1, 0 provides the output as 1 and 1, 1 gives us the output as 0. And to have these outputs, the respective expressions for perceptron are also shown here. Why this function is non-linear? If you look at this figure, see here the 4 points in the space are denoted here in red and blue. So red points are having the output as 0, whereas the blue points are having the output as 1. If you look at this figure, it is not possible to separate these positive and negative points with a simple linear function or a line, and hence this Boolean function is non-linear. If we try to use a perceptron to find the decision boundary, let us see here we are having the set of inequalities. First is W0 less than 0, W2 greater than minus W0, W1 is also greater than minus W0, and the fourth inequality is W1 plus W2 is less than minus W0. So if you look at these equations carefully, you can notice that the fourth equation actually contradicts the second and third equations. So point is, there are no perceptron solutions for non-linearly separated data like this example. So the key to take away is that a single perceptron cannot learn to separate the data that are non-linear in nature. Thus, the limitation of MP neuron that we posed earlier, that MP neuron cannot provide solutions for linearly non-separable data. Here the single perceptron also cannot provide the solution for linearly non-separable data. Now let us try to understand how perceptron learns. So let us assume that we are dealing with a supervised classification problem, and now we are going to see the perceptron learning algorithm, that is supervised learning. So what we mean by that? We are having the training samples provided with the associated classes, and with the help of that data set we are going to train our perceptron. So see here, we are having a perceptron. The perceptron accepts features of one instance as inputs. Let us assume that the training data set is having many instances, and each instance is described with a pair xi, yi, where xi is the ith training instance and yi is associated class or label. This instance xi is a vector and it comprises of, let us assume, n number of features. So whenever we present this training example to the perceptron, it accepts its features, say x1, x2 up to xn, as inputs. Associated with every input we are having the weight. Please note also we are having additional input that is meant for bias. So here x0 is equal to 1 and w0 is the bias in the form of weight. Thus for a given perceptron we are having n plus 1 inputs and n plus 1 weights associated. Both are the n plus 1 dimensional vectors, and this perceptron produces the output as y. So please see here, w is the column vector having the elements w0, w1 up to wn, and x is the input vector, once again a column vector having the elements x0, x1 up to xn. Now we know the expression how the perceptron computes the output y, but here we are slightly modifying that expression. See here, as y equal to 1 if summation over I equal to 0 to n wi xi is greater than 0, and y is equal to 0 if summation over I equal to 0 to n wi xi is less than 0. The reason behind modifying the expression can be explained using this figure. So let us assume that we are having few instances shown here in this figure, and we would like to separate out these instances in two classes. You can observe here that two samples belong to one class, say negative, and two samples belong to other class, say positive. And what we would like to do is, as the supervised learning algorithm, we would like to learn such that we can have a decision boundary that separates these samples into two classes, such that the samples towards one side of the decision boundary belong to, say, class negative, and the samples at the other side of the boundary belong to other class, say positive, and this decision boundary is denoted as the dot product of W and X equal to 0 or W transpose X equal to 0. So if the weighted sum comes out to be 0, these points lie on the boundary. So when we are going to put the labels as 0 and 1, if the samples belong to either of the sides of the decision boundary, and that is why we have modified this expression a little and we have removed the equality condition, because if the weighted sum is 0, the point lies on the decision boundary. The decision boundary can also be denoted as the expression of the line here, because this is a two-dimensional space, and the expression of the line can be written as W0x0 plus W1x1 plus W2x2 equal to 0. So with this background, now let me explain the algorithm for perceptron learning. So here we are having the set of samples in the training set, and using this training data set we are trying to train our perceptron. In our training data set we are having few samples. Those are positive, having label y equal to 1, those are denoted as P. Similarly, we are having the negative samples with class label y equal to 0, and those are denoted as N. So to begin with, we need to initialize the weight vector W randomly. So we need to have some initial weights associated with all those elements W0, W1 and so on up to Wn. So first step is to initialize the weight vector W with some random weights. Next, in this algorithm we need one parameter eta known as the learning rate. So the learning rate eta is a small positive constant, and that also we need to initialize at the beginning. And now comes the important part of this algorithm, the body of this algorithm. So we are having this algorithm as the iterative algorithm. So we are having a while loop with the condition while not convergence do. And what is the convergence condition here for this algorithm? As this is the learning algorithm, this algorithm is said to be converged when all the training samples are classified correctly. So till there is no convergence, we are going to iterate through. The first step in the loop is pick an example or instance X from training data set. Now if the instance X is a positive sample and W dot X is less than or equal to 0. So what is this W dot X? It is nothing but the weighted sum Wi Xi. So if this sum comes out to be 0 or less than 0, what does this mean? This means that if it is less than 0, then according to the expression, the output should be 0, that means negative, and if the sum comes out to be 0, that means the sample lies on decision boundary. So if these two conditions are satisfied, that means actually the sample is positive, but according to the perceptron condition, the summation comes out to be negative or equal to 0, then the computed class is negative. So there is a contradiction, and if there is a contradiction, then we need to update the old weight vector W as W equal to W plus eta X. So as I said earlier, eta is a small positive constant, and that is a learning rate. So if actually the sample is positive and it is being computed as negative or 0, then there is a contradiction, and hence we need to update the weight using the expression W equal to W plus eta x. Similarly, we are having the other condition. If actually the sample belongs to negative class and the dot product W dot x is evaluated as greater than or equal to 0, that means actually the sample is negative and it is computed as positive or 0, then here also we need to update the weight vector. And here the expression to update the weight vector is W equal to W minus eta x. So obviously, if the sample belongs to positive class and the weighted sum is greater than 0, then no need of updation of the weight. And also, if the sample belongs to negative class and the weighted sum is computed as negative, then there is no mismatch, and here also we need not update the weight vector. And this process continues till all the samples in the training data set are classified correctly. And once it is done, we say that the algorithm is converged and our perceptron is trained for the given data set. Please note here, the role of learning rate eta is to moderate the degree to which the weights are changed at each step while iterating through the algorithm, and typically it is set to some small value, say for example 0.1. I am going to explain this perceptron learning algorithm with one example, hand-coded example, so that you can have the better idea how this algorithm works. So we are having a very simple example here. So we are having a training data set with only 4 samples or 4 examples, 2 samples with class n, that is negative, and 2 samples which are positive, right? Now these 4 instances are being described by 2 features each. So capital X1, capital X2, X3 and X4 denote 4 training examples, and every training example has 2 features. Those are small x1 and small x2. Thus 4 instances are denoted by 4 vectors x1, x2, x3, x4 along with its associated labels or classes. So x1 and x2 belong to negative class, x3 and x4 belong to positive class. x1 is the sample 0, 0, x2 is given as 0, 1, x3 is 1, 0 and x4 is 1, 1. So if we look at pictorially how these samples are placed in 2-dimensional space, we can see here these samples x1, x2 belong to negative class and x3, x4 belong to positive class. Even though perceptron can deal with real values, to make it simple, we are having right now the values as 0 and 1 for inputs. And now we are interested in learning this data using perceptron, and we would like to find the decision boundary that separates the samples in 2 classes, positive and negative. So I hope you must have understood the question or the problem to be solved, and now we are having the solution here. Our perceptron can be modeled like this as shown in figure here. Our feature vectors comprises of two features each, x1 and x2. So these are depicted here as two inputs of the perceptron, and this third input is the spatial input for the perceptron having x0 equal to 1. Associated with all those inputs, we are having weights w0, w1 and w2. Perceptron is computing the weighted sum, and based on the condition it is providing us the output y. So here the input vector x is having three elements x0, x1, x2, and the weight vector w is having the elements w0, w1 and w2. So with this perceptron configuration, we are supposed to reconstruct our data as per our requirement. So now the feature vector capital X1, which was earlier having two elements 0, 0, now we are adding one more element x0 into this vector, and x0, as we know, it is always equal to 1. So capital X1 is equal to a vector 1, 0, 0, and the associated label y1 is equal to 0 or n, that is the negative class. Similarly, we are describing the vector x2. The original features are 0, 1, and x0 is being added as 1. So now capital X2 becomes 1, 0, 1, and y2, that is the class, is 0 or the negative class. On the similar lines, we can describe two instances x3 and x4 with three elements now 1, 1, 0 and 1, 1, 1 respectively, and both x3, x4 belong to the class positive. Thus y3 is equal to 1 and also y4 is equal to 1. Now as per the algorithm, let us assume that the learning rate eta is equal to 1. We are making the thing simplified just for understanding the working of the algorithm, and hence we are not picking up very small value for eta. Let's assume here for this example eta is equal to 1. Next we would like to initialize the weight vector, and hence the weight vector w is initialized as 0, 0, 0. Now let us once again write here the important rule for updating the weight vectors, because this is the key in our perceptron learning algorithm. So the rule says that if x belongs to p and w dot x is less than equal to 0, then update the weight vector w as w equal to w plus eta x, and if x belongs to negative class and w dot x is greater than or equal to 0, then w equal to w minus eta x. Here what we mean by w dot x, it is the dot product of two vectors w and x, and w dot x is given as the summation over I equal to 0 to n wi xi. So every time we need to compute this weighted sum for the computed weight vector and the presented sample x. Now let us iterate through the algorithm. So the first iteration, we are presenting the first sample x1 that belongs to class n or negative sample. So if we compute the sum w dot x1, here w is initialized to 0, 0, 0 and x1 is 1, 0, 0. So the sum, weighted sum, comes out to be 0, and according to our rule, if x belongs to n and the sum is 0, we need to update our weight vector w as w equal to w minus eta x. So original w 0 0 0 minus eta is 1 into the vector x1. So the new vector comes out to be minus 1 0 0. Now let us present the next sample, say x2, that 2 belongs to the negative class. Now once again we will be having the sum, that is the w that we have computed in step number 1, or rather iteration 1, and having the dot product of this w with the new sample presented, that is x2. So x2 is 1 0 1 and this w is minus 1 0 1. So the weighted sum comes out to be minus 1. And see here, we are having x2, that is the negative sample, and the sum is not greater than or equal to 0, and hence we need not update w, because the sample belongs to negative class, and as per the perceptron it is also computed as belonging to the negative class or 0 class. There is no mismatch, and hence we are not going to update the weight vector, and so the weight vector remains the same, that is minus 1 0 0. Now let us go to the next iteration where we are presenting third sample x3, which is positive. On the similar lines, x3 is 1 1 0 and w is minus 1 0 0. So the weighted sum of w and x3 comes out to be minus 1. Now as x3 belongs to positive class and the summation is negative, that means there is a mismatch of the original label and the computed label, and hence we need to update weight vector as w equal to w plus 1 into x3, and hence the w, new w, is computed as 0 1 0. Next, in the fourth iteration we are going to present x4 as the input. So x4 belongs to the positive class and it is having the elements 1 1 1, and the vector w is 0 1 0. That was computed in our third iteration. So the weighted sum of this w 0 1 0 and x4 1 1 1, the weighted sum comes out to be 1, which is greater than 0. So the perceptron is also saying that the sample is positive. So there is a match, and hence we are not going to update the weight vector, and we are having the weight vector which is same as the earlier iteration, and that is 0 1 0. Now all 4 vectors we have tested, but still we have not reached to the convergence, and hence repeatedly we are going to provide all those instances again and again. So in the fifth iteration, once again we are going to present x1 that belongs to negative class. On the similar lines, we are computing the summation which is 0. So once again we need to update the weight vector as w equal to w minus 1 into x1. 1 is the learning rate, and thus the new weight vector is computed as minus 1 1 0. The process continues. So in the sixth iteration, x2 is being presented, sum is minus 1, and there is no need to update the vector. So w remains the same, that of the earlier iteration. In the 7th iteration, x3 is being presented, that belongs to positive class. The sum is 0. Now here we need to update the weight vector w as w equal to w plus 1 into x3, and hence the weight vector is being updated as 0 to 0. Next we are presenting x4 that belongs to the positive class. The sum comes out to be 2, so there is no mismatch, and hence the weight vector remains the same. In the next iteration, x1 is presented again, then the sum comes out to be 0. The weight vector is updated as w equal to w minus 1 into x1. Thus the weight vector becomes minus 1 to 0. In the 10th iteration, x2 is being presented, summation is minus 1, so there is no mismatch, so the weight vector remains same. In 11th iteration, x3 is presented, the sum is 1, there is no mismatch, vector remains same. In the 12th iteration, x4 is presented, which belongs to positive class, summation is 1, vector is not changed. In 13th iteration, once again we are presenting x1 that belongs to the negative class. The summation computed is minus 1, thus no need to change the vector, and hence we can see that for all the samples and with the weight vector minus 1 to 0, we are getting the correct class of the sample, and hence all the training samples are classified correctly, so we can say that our algorithm has converged, and we are going to stop here. Let us once again have a look what we did and how we updated the weight vector. So if there is a mismatch for negative class, we are subtracting from the weight vector, and if there is a mismatch for positive class, we are adding the quantity in the weight vector. Thus the final weight vector that we have got after learning this perceptron is minus 1 to 0, and this is the objective of our perceptron learning algorithm, to find out this weight vector that actually defines this perceptron model. Now using this weight vector, we are supposed to find out the decision boundary. Let us denote this decision boundary as d of x. The decision boundary can be obtained by the equation, linear equation w0 x0 plus w1 x1 plus w2 x2 is equal to 0. This is nothing but actually the expression w transpose x equal to 0. So if we substitute the values of the respective weights in this expression, what we get is minus 1 into x0 is always 1, we know that. So minus 1 into 1 plus 2 into x1 plus 0 into x2 is equal to 0. By substituting the values w0, w1, w2 that we have computed and the value of x0, that is 1. Thus we compute the decision boundary as minus 1 plus 2x1 equal to 0, or by rewriting this we can say our decision boundary is 2x1 minus 1 is equal to 0. Now if we would like to plot this, or if we would like to geometrically represent our decision boundary, please look at this. This vertical straight line actually depicts this decision boundary d of x equal to 2x1 minus 1 equal to 0. I hope you must have understood how we have plotted this decision boundary. Here I am getting x1 equal to half, that is 0.5. So I am having this vertical line at 0.5, and this line actually separates the negative samples from the positive samples. Now once this decision boundary is obtained, if a test sample is being presented, then it is possible for us to find out the class of this test sample. So with this decision boundary, if our test sample happens to be towards left of this decision boundary, then we are going to say that the sample belongs to the negative class. Otherwise, if sample is towards right hand side of the decision boundary, then the class of the sample is positive. So let us try this with one test sample. So let us assume that our test sample is 0.25, 0.25. So small x1, small x2 are 0.25, 0.25. So our feature vector becomes capital X equal to 1.25, 0.25. Now we know the weight vector for our model, and we are having the values for x0, x1, x2 from the test sample. So substituting all those values in our expression w0 x0 plus w1 x1 plus w2 x2, we compute the value, that is minus 0.5. So the weighted sum is less than 0, meaning y, that is the class, is negative or 0. Thus we can predict the class of the test sample that is presented to our learned perceptron. I hope you must have understood this numerical problem that we hand coded especially to understand the perceptron learning algorithm properly. Now let us have the final comments. If the training data set is linearly separable and sufficiently small learning rate eta is used, perceptron learning algorithm converges. But if the training data set is not linearly separable, convergence is not assured. So what to do if the data is not linearly separable? So we are having the solution for the problem, and that is the delta rule, which uses gradient descent. The gradient descent algorithm we have used earlier, and we know how to use gradient descent. So we are going to make use of this gradient descent as a part of delta rule, and we are going to discuss this algorithm in the next session. So for today, let us stop here. Thank you.